All right, this is 2.2. Doesn't say it on here, but these notes should be labeled day number 1, as we will take 2 days to talk about synthetic division and the remainder factor theorem. This just gives a little description about synthetic division. You can kind of take that for what it's worth. For the most part, to really get the idea of synthetic division, it takes some examples. Okay, it's typically used to determine zeros of higher ordered polynomials. Okay, we have to find some alternative techniques to find zeros. So far, we've extensively practiced finding zeros of quadratics, which are oftentimes very reasonable to split into 2 linear factors. That gets harder to do as the degree gets higher. We can complete the square. That's a technique that doesn't work very well when the degree gets higher. And we have the quadratic formula, which doesn't work at all if you're not dealing with quadratic. So synthetic division is kind of this tool that we use to help us kind of factor and find zeros of higher ordered polynomials. It's a useful little useful tool for us to have. All right, let's say we want to divide these 2 polynomials. Okay, x to the third plus 5x squared plus 5x minus 2. We want to divide that by x plus 3. Okay, this divisor is in the form of x minus a, which means we could use synthetic division. Okay, when I do it, the remainder will equal p of a. Okay, now in this case, a is negative 3. Okay, because it always refers to the form x minus a. If you want to think about it this way, I could rewrite that little factor as x minus negative 3. Okay, so again, here's how synthetic division works. We have negative 3 out here. 1, 5, 5, and negative 2. Okay, the 1 comes down. I take negative 3 times 1 and get negative 3. Adding those, I get 2. Negative 3 times 2 is negative 6. 5 plus negative 6 is negative 1. Negative 3 times negative 1 is 3, and adding those I get 1, and there is my remainder. Okay, now the way this can be used to check for zeros is if this remainder comes out to be 0, we've got ourselves a 0. In this case it doesn't, but what the remainder theorem says, that p of negative 3, if I were to put that in as an x value, the y value is 1. Okay, it tells me some information about this graph, mainly what the ordered pair that goes with x equals negative 3 is. In this case, y is 1. It's not a 0. All right, not a 0, which is fine. Synthetic division can still tell you other stuff besides the zeros, but I don't have a 0 in this case. All right, next we can use this fact to check for factors. Okay, kind of a nice little thing to do. All right, for example, if this were a factor, x minus 2, that would mean that x equals 2 is a 0. Okay, you should always have factors and zeros, associated with each other. Okay, if x minus 2 is a factor, then x equals 2 is a 0. So if I take 2 and set up some synthetic division, so 2, 5, negative 8, negative 17, negative 6. Okay, 2 comes down, 2 times 2 is 4, 5 plus 4 is 9. If you're feeling confident with synthetic division, this isn't a bad time to just pause the video and give it a shot yourself and see how it works out. 2 times 9 is 18. Negative 8 plus 18 is 10. 2 times 10 is 20. Negative 17 plus 20 is 3. 2 times 3 is 6. Negative 6 plus 6 is 0. Okay? Again, what this tells us, several things. P of 2 is 0. Oops. I'm still thinking of the previous problem. I should not be calling this polynomial P. Its name is M. M of 2 is 0. Okay? This polynomial has a 0 of 2, and that means x minus 2 is a factor. Okay? So this is a common thing that we do with higher ordered polynomials. Instead of factoring, we use this technique to generate some possible factors, and then we can use synthetic division to check to see if they are. Okay? It's just we go about things a little bit differently when the degree of our polynomial is higher than 2. Now, let's try this again. But in part B, let's check the factor x minus 1, which means we are going to check to see is 1 a 0, and thus is x minus 1 a factor. Now, here's something kind of nice that I could do. Okay, I saw from my first round of synthetic division that 2 is a 0 and x minus 2 is a factor. Okay? Because that worked, and only because that worked and it divided evenly, I can use the quotient that's left over, and I can just check 1 with those 4 numbers instead of having to use the 5 numbers like I had to use in part A. Again, when I'm referring to 5 numbers, I'm talking about these. Okay? Means I have one less step to do in synthetic division. Okay, it's not a ton of work that we avoid here, but you know, it's something. If you had to do 5 rounds versus 4, I'd take 4. Okay, so because that one divided evenly, I can just use the quotient and start from there. Okay, pull down the 2. 1 times 2 is 2. 9 plus 2 is 11. 1 times 11 is 11. Sum is 21. 1 times 21 is 21. And we get 24. Okay? This means m of 1 equals 24. 1 is not a 0 for m. X minus 1 is not a, running out of room, factor. X minus 1 is not a factor. So we check 2. X minus 2 is a factor. X minus 1 isn't. Again, this is more than the normal process of how we find factors and break polynomials down into factors when their degree is higher than 2. Okay, when they're 3, 4, or 5. Okay? More to come in 2.2 day 2. What we're mainly going to do there is just check for factors a lot more, break higher ordered polynomials down into their factors a lot more, check for zeros a lot more, and just practice a ton of synthetic division. Okay, very similar to what we just did here.